talk mechanical behavior, deformation, and things like that. Okay, a couple of things I wanted to go over. This is we talked about slipping on different crystalline planes, and that leads to anisotropy. But I came across this in one of the books I was looking at. If you just take a bar that would be a single crystal, and you were to pull on it, it would, if it didn't have any bending, and it would just start shearing on certain crystallographically preferred planes, you would actually get a translation off to the side. And this is just a demonstration of that. In fact, when you actually pull on a bar, a single crystal, you actually will pull in the same tensile direction because of the stiffness of the machine that's pulling it. And that requires that you also get a bending as well as a shear. Okay? Which you can see here. It's just a nice drawing to show that even when a simple tensile test is not so simple. I remember back often saying that once when I was a student, that and he'd been looking at tensile tests all his life, and he'd concluded that the tensile test was, even though it seemingly was the most simplistic test you could imagine, but actually when you get into the details of it, it's extremely complex. And we're going to go through some of that a little bit later. This is another picture when I was going through Hertzberg's book. He had of a Sharpie bar that fractured, but it's in a steel. I told you that the texture that we develop because of this anisotropic behavior gives you a fiber orientation, just like wood is anisotropic. Okay, and you can see the fibers in this particular piece of steel, so far as that goes. So that's just sort of enrichment, or whatever you want to call it. We've been talking about sheet metal properties, and we're starting to talk about superplasticity. We have N values, R values, and M values. N is the work hardening coefficient, R is the anisotropy ratio, and M is the strain rate sensitivity of the material. And superplasticity, we looked at the forming limit diagrams. For certain types of metals, instead of having when the biaxial strain in the transverse direction E2 is 0, you might have 30 or 40 or 50% elongation in a regular old tensile bar. But in a superplastic bar, you can have 100%, 250%, 300%. And in fact, when you start stretching or compressing in the transverse direction, you actually can get even more strain, and that allows you to do all kinds of sheet metal forming operations when it's superplastic, but it also helps you even when the material is not superplastic. So then to review a little bit of superplasticity. Superplastic forming diffusion bonding, in fact they call it SFDB for superplastic diffusion bonded, okay, SPF, superplastic form diffusion bonded, was something that the Air Force put a lot of money into after they realized that they could form titanium this way. Let's just look at this one. You basically would form two sheets and you'd weld them together in a hermetic seal. You'd put them in a die cavity, and you would, since it's hermetically sealed, you actually would put pressure in between the sheets as you heat the whole thing up. And it might take 10-20 minutes, it might take an hour or 2 hours depending on the temperature and the alloy that you're using. And your dies are going to have to be operating, I'll give you some temperatures in a little bit, they could be operating 800-900 degrees centigrade, but you actually can form a very complex part. Okay? The bond, this is one of the diffusion bonds between one of those areas, and you end up getting an excellent bond. Titanium is one of the easiest materials to diffusion bond, and it also happens to be superplastic. And so you can see a finer grain structure in the top rib, stiffening ribs, and in the outside shell you can see a coarser structure. This is a Rolls-Royce alloy or sample. Now, superplastic forming is actually a creep phenomena in the metal. This is just for aluminum alloys, but these are different strain rates from 10 to the minus 6, okay, to 10 to the 5th. So this is it's 100,000 per second, which is, if you want 10 million% deformation per second. This is pretty fast. This is sort of ballistic velocities over here. And over here at 1/1,000,000th or 1/100,000,000th% per second strain rate, this is pretty slow forming. Tensile testing and stuff would be in the 10 to the minus 3, 10 to the minus 4, and your grain size can vary. They've got orders of magnitude here, but basically aluminum, zinc, magnesium alloy, some of your 7000 series aluminum alloys used in aerospace, they may have grain sizes on the order of 20 microns. As you get finer and finer grain, creep becomes easier and easier. In fact, we try to get rid of grains when we want to get the best high temperature creep properties. We actually go to single crystals to completely get rid of grain boundaries. Well, if you want to get creep and make things super plastic, you want fine grain, and this shows the fine grain size as a function of strain rate for aluminum alloys. This is powder metallurgy aluminum alloys. Now you're getting into superplastic forming strain rates of a tenth per second, which means that you're going to get 100% strain in 100 seconds. So in a couple of minutes, you're actually going to pull this thing. It's almost like my taking the clay and pulling it before your very eyes. That's the type of 10 to the minus 1, 10 to the 0 type strain rates, okay, to give you some idea. If you get very, very fine grains, physical vapor deposition, if you go to mechanically alloyed aluminum, which is a way of beating it in a ball mill and then consolidating it by extrusion, you get even finer. And then if you go to amorphous or nanocrystalline, and you get grain sizes down here in the 1,000 angstrom range, you get superplasticity and you get high strain rates. In this region, you have negative exponents of the strain rate. Here we have positive exponents, and then we have impact superplasticity. So you can have superplasticity in all these alloys at different strain rates. But it's basically a creep phenomena. This is just looking at aluminum alloys. Now, a question that I get, I would say, about once a year from someplace is someone will claim that the metal was deformed so rapidly that it was very highly strengthened, okay? Well, superplasticity basically says, well, you can deform it very fast, but you're not necessarily going to be stronger, you're going to be weaker, okay, at higher temperatures. But the question is, and I don't know if I've said this, we do impact extrusion, okay, and we do ballistic. Well, the Army and other people do ballistics where they're doing things at very high strain rates, and the question is, at what strain rates does the metal start to become stronger? And I think I may have mentioned this. It's at the strain rates at which you start to compete with dislocation motion speeds. And the dislocations go at about 1/3 of the speed of sound in the material. And so when you're at movements of the metal on the order of 1,000 meters per second, which you can be in ballistic velocities, things get stronger because the dislocations don't have time to move. But in general, you know, in an automobile crash or a building collapse or something like that, the metal's not stronger. I mean, that's on a very slow time scale compared to dislocation movement. Okay, so, but you hear this little old wives' tale all the time about, oh, it was so fast that the metal was much stronger. No, not unless you're talking ballistic velocities. Okay, this I mentioned before, Conform, and this is actually a commercial Conform machine. Conform is the way they made, and I passed this around, this trolley wire, which I mentioned before. Conform is an extrusion process that was developed in the late 60s, early 70s at a British National Laboratory, an energy laboratory doing work for the nuclear business, and some guys are sort of doing basic research. And you basically just kind of pour some powder into a channel and you rotate it. It's a rotating channel. And at the end of the channel, just by friction, all this powder is being consolidated and churned together. The actual working end of this is this end right here. It's just a big circular thing. You got powder filling in here. This is the motor to run it. It's a big motor, okay? And you'll just, it stands Conform stands for continuous forming. As long as you pour the powder in, you're just mechanically working it, and you're getting tremendous redundancy. I mean, if you want to try to figure out some delta for this operation, it'd be like 1,000. I mean, it's just, you're kneading the powders and cold welding them together, and you ending up with a tremendous amount of mechanical work in the alloy. And that, it turns out, for these alloys, I determined you end up getting what's called dynamic recrystallization. It comes out hot, okay? You don't want to touch it when it comes out, this piece of copper, because it's been all this work that's going into it, and it'll come out 400 or 500 degrees, you'll burn your hand. But at that 400 or 500 degrees, for this particular alloy, which has got a little bit of silver in it, you get to the recrystallization range. And so you're mechanically working it, you're also nucleating fresh grains at the same time, but then you're continuing to mechanically work it while you're nucleating the grains. That's called dynamic recrystallization. And you can get fantastic properties, super fine grain size, which you need for super plasticity, and fantastic material strength and toughness, because fine grain size gives you good toughness if you know the Hall-Petch equation, which hopefully you may have learned somewhere else. But anyway, dynamic recrystallization is used in the steel industry to make sheet and plate material, where they have rolling mills now that have enough force and they roll the steel at lower temperatures. Instead of rolling them at 1100 degrees centigrade, they roll, which is kind of like forging temperatures, they can roll them at 1400 degrees Fahrenheit. And so you're squeezing the stuff, deforming the grains, and it's recrystallizing even while you're deforming, and so you can get fine grain size. And you get much better properties. And that's what is the basis for most of our high-strength low-alloy steels, is be able to get dynamic recrystallization. Now, as I looked up Conform, I actually tried to do Conform to make some superconductors back 30 years ago, and it didn't work very well. But if you look at Conform now on the web, for the production of copper flat strip, copper bus bar, commutator connectors for motors, trolley contact wire, which is what this is, okay, and other solid copper conductor. You can do it with aluminum, but it's easier to just extrude aluminum the old-fashioned way. Aluminum is at a low enough temperature. Obviously, this is good for copper alloys. People have tried to do it. I tried to do it for a mixture of copper niobium alloys, and I just broke the dies. It couldn't, the niobium just strengthened things too much, and I couldn't come up with a steel die that wouldn't break. But when you've got something relatively soft that undergoes dynamic recrystallization, you end up with some very good electrical conductors. However, the only two countries I could find that have Conform machines, I did it because they had a Conform machine, the North American, in the early 70s, the North American company that was trying to sell Conform was located down here in Pawtucket, Rhode Island. Okay, so it was close enough that I could go do some research down there. But the only two countries now that have these great big machines are India and China. Why? Because they still build railroads. Okay, and use trolley wire. Most of the rest of the world, well, we just buy it from them if we need it. So it's sort of a specialized process, but it is a very high redundancy process. Now, if I'm going to try to get something that's super plastic, I need something that's going to help me maintain the fine grain size. And one of the problems with very fine grain size is the grains want to grow, and the smaller they are, the bigger the driving force for growth, because it goes as the inverse of the radius. The smaller the radius, the bigger the driving force to grow larger grains. And this is a plot out of for the titanium, alpha beta titanium alloys that are super plastic, and it shows you The elongation in percent, well, we're getting up to 1,000%, so that's certainly superplastic for a metal. But you get a peak somewhere around 30 volume percent. Does anyone know what's significant about 30 volume percent for just out of geometry, but it comes out of metals if you've studied solidification of composites or things? Anybody have an idea? I don't know if you run across this, but it turns out if a structure is controlled by surface tension, you can either get a bunch of little spheres embedded in a matrix. It shouldn't be looking like a happy face anyway. Or you can get it so it wants to form plates or fibers embedded in a matrix. And this is or actually cylinders, okay? Plates or cylinders. But just think of these as little cylinders. And the question is, will the alloy want to form spheres, or will it form cylinders if you heat treat it, recrystallize it, and let the grains grow? It turns out that the minimum surface energy for a mixture of spheres, if you have less than 30 volume percent of your second phase, is spheres. At above 30%, you're going to want to form fibers. You can do a minimization. And actually, if you go through, I had to do this as a student. What do they call it? The method of Lagrange multipliers, variational calculus. Okay, you're MIT students. You can go look it up. But basically, if you want to if you can write down the differential equation and then do a minimization on that, you basically use the method of Lagrange multipliers, or you can use variational calculus, and you can prove at 31 volume percent, okay, exactly, the system would prefer to have cylinders above 31%, and below 31% it would rather form a bunch of spheres for the second phase. And then of course these things can coarsen to something else. But the point here, when I looked at this, I said, oh, this is basically where we're getting structures that can be stabilized by two interpenetrating phases in the alpha beta mixture. So if I look at titanium and the microstructure for a superplastic alpha beta titanium alloy, they're not exactly spheres in this case for other reasons. One's hexagonal close packed, the alpha phase, and the beta phase is body centered cubic. But in any case, you get something where the grains can't grow rapidly and coarsen because the beta grains, or the alpha grains, are completely surrounded by the beta grains at around something just under 30%. Okay? So it's harder to get superplasticity in a single phase alloy, okay? And in a single phase alloy on either side, but it's easiest to get superplasticity when you have about 30% of one phase inside another, because that 30% phase is completely encapsulated in the second phase, as not exactly spheres necessarily, but something close to spheres. If you had a bunch of fibers like this, it wouldn't have a lot of surface energy. This is the way to get the maximum surface energy, because superplasticity is really a creep phenomena of the grain boundaries sliding against each other. So you want as much surface energy as possible. You want as much as many grain boundaries as possible to get the most superplasticity. Yes?
Why is there not a drum peak at 70%?
Pardon me? Well, why isn't there one at 70%? Well, I guess there would be. Okay, but in this case, I'm sure that in the titanium it has to do with the diffusion of the different elements in one phase versus the other phase. So you're right. In theory, you could say there should be one at 30 and 70. I'm sure the reason there isn't one at 70 is probably because, well, I don't know exactly. It's a good point. If it's just a simple geometry, yes, there would be one at 70. If you also include the coarsening phenomena, the diffusivity in the different phases, then I'm sure that's one of the reasons we get rid of the 70% peak. Okay? But if you look at the structures of these alloys, you'll find that they're about 30% on one phase and another. For example, if I went back to the aluminum zinc, this first superplastic thing that Backoffen did, it's about, I can't remember if it's 70% zinc or 70% aluminum, but it's right around 30%. If you look at the phase diagram, it's right around 30% of one phase and another phase. And that's not a happenstance. That basically comes out about the fact you're trying to introduce the most grain boundary area per unit volume and have one phase stabilize the second phase. But you're right, you should have two peaks if you didn't have diffusion effects also. Okay. Well, solubility and diffusivity. Well, the solubility and the diffusivity are interrelated, right? Right. You have to look at the whole phase diagram. Usually it's one phase in another phase, and nature chooses which phase wants to be the minor phase and which one wants to be the major phase. If the solubility and everything else were all the same, I think he's right, you should get two peaks, okay? Or maybe it kind of becomes one big thing in the middle, okay? Maybe the 50% in between isn't much of a trough. A lot of scatter in that data. But the point is, at 30, from a pure geometry, nothing else considered, you get the most grain boundary area for two phases interlocking in one another. It's hard to get superplastic alloys that are single phase, okay? You kind of need the stabilization of the microstructure by having the two phases intermixed. That's what I'm trying to get across, okay? Now here is some composition of superplastic alpha beta alloys. 6,4 titanium, that is the workhorse titanium alloy invented over here at Watertown Mall, okay? Actually it was the Watertown Arsenal until about 20 years ago when they had the bracks. It died in the first round of bracks, but it was built before the Civil War to make weapons for the Army. They made cannonballs there during the Civil War. In any case, in the 1940s, they invented titanium 6 aluminum 4 vanadium, which is superplastic in the 900 degree centigrade range. There's a number of different titanium alloys, but they're all in this 800 to 1,000 degree centigrade range, and they have elongations at strain rates of 10 to the minus 4 per second in the 300 to 1,000% range. Okay, so lots of different alloys, but they're all going to be processed in a way to give you some sort of microstructure that looks like a bunch of 30% one phase and another phase, okay, approximately. Now, there are lots of different alloys that behave superplastically, not just titanium. Aluminum copper alloys, notice 33% copper. I mean, it actually is the copper intermetallics, but nonetheless, if you started looking at the phases, zinc aluminum, here's the zinc aluminum, zinc 22 aluminum. So this alloy is 70% zinc and about a third aluminum. 22 by weight, but volume percent, aluminum is lighter than zinc and stuff. And that's superplastic at 200 to 250. It's one of the reasons Backoffen did it. He liked to use low temperature systems, it's easier. That occurs over about 2 orders of magnitude in strain rates. These two are what we call duplex stainless steels. They are both FCC and BCC, and they have a duplex structure. They are in the 30% range again, because you need that to stabilize. You can't, just because you can make these stainless steel superplastic, if we could make 304 stainless superplastic, believe me, we would. It's the workhorse alloy, okay? But you can't do it. You have to use a duplex stainless because it's best to have this kind of 30% concentration. IN 100 is nickel-based superalloy, 738, 629. This one actually is a copper base. IN just means international nickel. And then nickel aluminum bronze, which is basically a copper base alloy. So you got copper, aluminum, iron base, and of course we have titanium base as well, superplastic alloys. But in general, they're going to be things that occur at of about 30% one phase and another phase. It can be 30% plus or minus 10 or 15%, but it's going to be in that range. Because you have to stabilize the small grain size and not have it just take off on you. The superplastic temperature, this is the strain rate exponent. Remember, M is what controls superplasticity. Typical M values for metals are down in the 0.02 range. I've showed you that data before. And so we're down here. This is 0.1 and 0.2. And as you get above, this is T over Tm, that's the melting temperature, so this is what's called the homologous temperature. As you get up to the creep regime, creep usually is considered above 6/10 of the melting point for a homologous temperature. Nickel-based alloy, titanium, 304 stainless. Now, even 304 stainless, you'll get a bit higher M value, but it's not superplastic because this isn't really superplastic. 0.2 is not really superplastic. You get higher elongation. Things start to stretch more, but it may only be a 50 or 60 or 70% as opposed to a 30 or 40%. But just in general, the M value goes up rapidly once things get into the creep regime, even if they're not superplastic. Okay? This is just for a couple of aluminum alloys, again showing this. If you do everything in Kelvin, you would find this is the same homologous temperature, strain rate sensitivity M versus the homologous temperature. It is a creep phenomena. If you look at, this may be the best version I found. You can have diffusional creep, superplasticity, or power law creep, and this is the log of the stress. And so actually this is going to be a lower temperature, this is going to be an intermediate temperature, this is going to be a high temperature. Here you have, that should be 0.1 or 0.2, okay? Low M values. When you get a high M value, like a half or greater, you get superplasticity. And when you get into just regular creep at high temperatures, you have lower M values. And so there's different types of creep. There's a book that I looked to see if I could buy it. It's in the library that Mike Ashby wrote, where he called Deformation Maps for Creep. And they look like this. This comes out of Hertzberg. But Michael Ashby used to be at Harvard. He used to be a lot of places. He ended up at Cambridge University and retired a couple of years ago. He's very prolific. He's written many, many books. He has a materials selector program that you can buy for $50,000. It works pretty well, okay? But in any case, he's one of the top metallurgists in the world for the last 30 or 40 years. Top half dozen metallurgists, let me say, okay? He really is among the very best. He came up with these kind of broad scale ways of looking at things. This is the normalized tensile stress over orders of magnitude versus the homologous temperature, and this is a creep diagram. He had a student when he was at Harvard do a doctoral thesis on developing these creep diagrams, and I think that ended up as this book. I wish I had a copy of it, but I couldn't find it on Amazon. But the library has one for all kinds of different alloys. But this is the theoretical shear stress up here. If you're stressing things very rapidly, you're just going into the lab and wham, okay? Or I take this piece of clay and I just shear it like that, you know, at those types of strain rates. If I go slower, I can get into, these are kind of dislocation glide type of frequencies. Here's the elastic regime, because this is stress versus temperature. At lower stresses, I'm not plastic. I'm getting plastic once I go above here. But in the elastic regime, as I go up at higher in temperatures, I'll get dislocation creep, diffusional creep, which is named after Bob Coble, who was a professor in this department. He figured out how to make better light bulbs at General Electric. He graduated from MIT, went to General Electric Research, invented Coble creep, and came back as a faculty member when I was a student. And Nabarro creep. Nabarro is a South African metallurgist who came up with an explanation of grain boundary creep. So Nabarro creep is a grain boundary creep. Coble creep is a variation on Nabarro creep with a different type of diffusional mechanism. And then dislocation creep is movement of dislocations within the crystal rather than at the grain boundary. So there's different ways to look at the dislocations, but in any case, if you look at, again, this creep phenomena as a function of temperature and strain rate, stress and strain rate, you had superplasticity in the middle, you had diffusional creep, and you had power law creep over here. Power law is kind of Nabarro herring and Coble creep. And you have, if you look at the M value plotted in the same region, you see you get a peak in your M values somewhere around 10 to the minus 3 at intermediate stresses, but it is a form of creep. But it gives you a very high M value. If you want to look at that same type of plot, for this is a bunch of aluminum copper eutectic alloys, I guess. Okay. This work was done by David Holt and Backoffen. Holt was hired as an assistant professor to work with Backoffen. He taught me part of Backoffen's course with Backoffen. He didn't get tenure at MIT. He went off to become an Episcopalian minister, as I remember. Okay. And he used to do metallurgical consulting on the side. Anyway, and I don't know what happened to him since then. I think he may have, I think there's some relationship. Carl Thompson's wife's sister is married to Dave Holt or something. I don't remember. Anyway. But anyway, here are your M values. This is your M values as a function of strain rate. Around 10 to the minus 3, you start getting these things that are above 5. And that's where you're getting, when you get above 5 on your M value, you're getting to useful superplasticity. Okay? But exactly which alloy, what grain size, looking at the grain sizes here, you're seeing grain sizes 1.7 to 7.7 microns. If you know anything about grain size, any grain size less than 10 micron is a very fine grain material. Most commercial alloys will be in the 25 micron grain size, okay, just because of the heating values and the way they're formed and everything. So here's activation energy for self-diffusion and creep in numerous metals in ceramics from Johannes Wertmann. Let's see, was Wertmann at Northwestern? Anyway, or University of Virginia, I can't remember. He's Northwestern? Okay. He and his wife are both tenured faculty, okay, at Northwestern. There's another pair at University of Virginia, husband and wife combo. There's another one at Penn State in materials, but anyway. Okay, so you were at Northwestern, I think. Okay. Anyway, Johannes Wertmann is a very big name as among physical metallurgists. Oh, that's right, because Julia Wertmann used to be on our visiting committee years ago. Okay, anyway. Okay, so anyway, this is the activation energy for creep. This is the activation energy for self-diffusion. And you can see over lots of materials a very good correlation between activation energy for creep and self-diffusion. So it is a diffusional process as atoms are moving around at the grain boundaries and changing the shape of the grains, basically. All you've got is, you've got atoms moving at the grain boundary. So if you started out with all equiax grains and you put a stress on it, now the atoms are going to move to the tensile stress direction and away from the other direction. Now you're going to get elongated grains. Okay? So it's just a diffusion phenomenon. There are lots of problems with trying to get fine grain size. This comes out of Backoffen. It's sort of at the end of his book, which he published in 1972, which is not all that many years after he discovered superplasticity, about 10 years after he discovered superplasticity. And you sort of see in the back of his book, this is sort of an afterthought. He was still thinking about this whole problem of how do you maintain fine grain size. So you can talk about D in millimeters, diameter of grains in millimeters. You can think of it in D to the minus 1/2. That's the Hall-Petch equation. If you're a physical metallurgist, you know that Finer grain sizes give you higher strength and higher toughness. This is in millimeters. This is inches to the -1/2. Here's D in inches. And then there's the ASTM grain size number. ASTM, really the steel guys years ago, came up with how many grains per square millimeter at 100x in a microscope or something. Okay, if you want, I could bring in the plates of the ASTM grain size. But a grain size in a forging or a casting might be around 0 or 2. I mean, the grains are big. You can see them, okay? Centimeter in size. A typical structural steel might be a grain size of 8. That might be your 25 microns or so. 10 or 12 is a high-strength low-alloy steel, where we get this dynamic recrystallization to try to maintain fine grain size. Same type of thing they did with Conform in the trolley wire. Okay, so you can get 10 to 12. Sometimes if you put in some precipitates too, you might get to 13. But if you really want to get super plasticity in steels, you got to be down here in the 16, ASTM 16 grain size, where you're getting down to, in microns, you're going to get down to 1 to 5 micron, or 1 or 2 microns grain size. Okay, that's the 16 range. I've never seen a steel with ASTM 16. Okay, about the finest I've ever seen is ASTM 13, but it would start to act like a superplastic material. The problem is if you heat it up to the superplastic temperatures, you're going to find that the grains grow, and that's back off his next plot where he's trying to think. You can kind of see him trying to think globally about this whole thing. Lifespan of succeeding generations of grains at different homologous temperatures to keep what you want each time you try to, well, let me back up. What he was doing here, if you cycle around a phase transformation, like the alpha-beta phase transformation in titanium, or there is a eutectoid phase transformation in aluminum zinc, if you cycle from alpha phase to beta phase and back down, you get recrystallization as you go from one phase to the other phase, as you go up and above and below this phase temperature transition. You have it in titanium, you have it in steels, you have it in the aluminum zinc alloys. You don't have it in every metal system, but if you want to get a 50% reduction in grain size every time you cycle through the temperature, to just do thermal cycling to get finer grain size, this is what happens. And Backhoffen basically plotted all this for 1/10 of a millimeter grain size, which is ASTM 4, which is pretty coarse grains, and he shows that depending on the number of cycles you do, 2, 4, 6, or 8, you're going to have to be doing cycling between temperatures within a second or two. Well, that's not very practical. Not when you got a great big thing that takes tens of seconds or minutes to get the heat to penetrate in, right? So basically, Backhoffen's in the in the late 60s is sitting there thinking, how can I get fine grain size? Now, since then, people have realized that this kind of 30% one phase and another phase helps stabilize the grain size. You get people like Professor Shu, who made part of his tenure basically on working with ultra-fine grain metals, where he used titanium. Well, a lot of his stuff, his company's based on a nickel tungsten alloy, where the tungsten, it gets into not only volume fraction, but solubility and diffusivity. Nickel and tungsten have lousy solubility in each other, and tungsten's got lousy diffusivity because of its high melting point. And so Professor Shu has been able to stabilize very fine grains, but it took 30 years between Backhoffen and Professor Shu to people to be able to get to ultra-fine grain materials. But some of those alloys that Professor Shu has should have some excellent forming characteristics in certain temperature ranges, as long as, but it's sort of a race. Will the grains recrystallize and grow bigger before you get to form it? Okay, so you know, you got to do your mechanical shearing before the grains get so big that they lose their elongation capability. Okay, I guess I bothered a few people when I asked you to talk about, for your presentation, to think about production quantity, and I never discussed it. But to me, I just or automatically, when someone comes to me about a production process to make some material, one of my first questions is, how many do you want to make? Are you going to make one? You're going to make 100? You're going to make 100,000? Okay? Because what process you choose is going to be dependent on how many parts you make. So if I want to make some complex egg crate construction out of titanium for some fancy aerospace application, and I'm going to make less than 10, so let's say it's the space shuttle, the unit production cost versus the production quantity for space shuttle parts, I'm going to make them by hand. I'm just going to get a great big forging, I'm going to get a milling machine, and I'm going to hog it out and have a buy-to-fly ratio of 200 to 1. It's going to cost a fortune. Space shuttle cost about $5 billion last time we bought one 30 years ago, right? Now you can't even buy them, and they fight over them. This is in a meeting in Houston on Thursday, and the people from Houston were very upset that New York got one of the leftover space shuttles and they didn't get one in Houston, right? Well, that's where the control was. Well, Houston, if you'd done a better job, we wouldn't have lost 2 of them. Anyway, the superplastic methods are competitive in a production quantity somewhere between 100 and 4,000 or 5,000. Well, now we're talking about aircraft, right? How many F-22s or Raptors are we supposed to make? 183. Well, gee, we're right in there, right? Superplastic forming is great, right? It only cost us $250 billion, right? Or whatever the number is. If you start getting into high production volumes, you're not going to use superplastic forming. It's a slow process. It might take an hour or 2 in the furnace to get one part. If you're going to make 200 parts in a year, no problem. Okay? Or 1 part a week, no problem. But if you're going to make 1 million parts a year, you're going to have an awful lot of furnaces. Okay? So superplasticity has sort of an important niche. It just happens to have an important niche in the aerospace market, which is a very important market. Any questions? That's superplasticity. Now we're going to go on to something else. So we've spent more time on superplasticity than maybe its inherent importance, but it illustrates lots of microstructure and principles of mechanics of forming. Let's talk now about just plain old deep drawing again. And you know, here's my set of deep draws where you go from a round circular blank and you do the first draw, the second draw, third draw, and the fourth draw. And these have all been cut off the end. I don't know, back often's dead. I can't find out where those came from. But in any case, this is something that someone came to me, actually Farberware is the company, came to me, and looks like I forgot to move a picture up to somewhere else. But in any case, Farberware came to me 15 years ago through the MIT Industrial Liaison program, and they said, we make these very expensive pots called Millennium Cookware, and we've shipped them to Japan, and lo and behold, when they get to Japan, they're cracked. And in fact, I didn't know that this was in Hosford's book at the time, but this stainless steel cups with stress corrosion cracking in a laboratory atmosphere, within 24 hours after drawing, the cracks are perpendicular to the residual hoop tension stress. So they had that. The Farberware pots had cracks like this, and they didn't form, well, I don't know if they formed within 24 hours, but they put them on a boat, they shipped them to Japan, and when they came off the boat, they had cracks running down here. This, if I pass it around, There's a few cracks around here, more than that. Well, there's two here. There's two here, and there's one. Maybe it's only got, no, it's got three right there. Okay, so they asked me, why do we have these cracks? And so I went and got my magnet, and I said, because you've changed the structure of your steel. It's very magnetic up here, and it's not magnetic down here. Right? I'm going to pass that around so everybody can. And I said, you've got hydrogen cracking. And they said, what's that? And I said, well, if you get hydrogen into your steel, there's two types of steel. There's 18-8 stainless, which is 304 annealed. And if you strain 304 stainless steel, you will get work hardening. Maybe I messed this up again. Yeah, okay. You'll get work hardening that causes the steel to transform. This is actually a 301 stainless. This is out of back often. This is the stress, 50 KSI yield stress, and then, boy, look at this work hardening rate. It will go up above 200 KSI, and this percent M is the percent martensite. 301 stainless steel is a trip steel, transformation induced plasticity. So it goes from face-centered cubic non-magnetic to body-centered cubic ferromagnetic. Martensite is ferromagnetic. And I just, right in front of my office, this is probably pre-1995, I just got my magnet out and I bang, 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 showed them how the different magnetism going up the wall. Why different magnetism? Different amounts of strain. The material, when they were drawing that, the material down at the bottom doesn't get strained at all. The material right here going up the side is hardly strained very much. The material up here at the top got drawn in and had lots of deformation. And so you have a variation in mechanical properties. Hosford shows, he calls it stress corrosion cracking. It's actually hydrogen embrittlement. But that's another thing. 70% of the time, metallurgists don't make a distinction between stress corrosion cracking and hydrogen embrittlement. There is a difference. One occurs at the anode, one occurs at the cathode. I learned that in a very difficult way. For 2 weeks, I was trying to crack a piece of steel in a little test, and we were applying a battery to try to reproduce the cracking. I couldn't get it to crack, and the literature said it was stress corrosion cracking. Corrosion occurs at the anode, right? So I had the piece as the positive piece, and I couldn't crack it, I couldn't crack it. And finally I thought, I wonder if this paper's wrong and it's really hydrogen cracking. So I reversed it to polarity, made it negative, and within 1 hour I had a crack. I wasted 2 weeks' effort because some metallurgist called it stress corrosion cracking, and it was really hydrogen cracking. There is a difference in polarity. 70% of the metallurgical literature makes no distinction between the two, but there is. One is a corrosion phenomena occurring at the anode, the other is a hydrogen embrittlement phenomena occurring at the cathode. Okay? I knew that was true, but I hadn't thought about it. I just assumed the people in the literature knew what they were talking about. And here's an example. Hosford doesn't know what he's talking about. He calls it stress corrosion cracking. It's actually hydrogen embrittlement. Because what's the corrosion for stainless steel just sitting on a laboratory bench? And so I said to the guys from Farberware, I said, I don't know where you're getting your hydrogen. How are you getting hydrogen into your steel to cause this cracking? And they said, well, would it have anything to do with the fact that to put the Teflon coating on, we spray stainless steel powders on the inside surface to make a porous surface to impregnate the Teflon? And we do that in an argon 5% hydrogen atmosphere? I said, oh, yeah, that could be a source. Okay, duh. Okay, so there we had it. That is hydrogen cracking. It's delayed cracking. It didn't exist when they put it on the boat. By the time it got off the boat in Japan, the hydrogen had done its dirty work. Okay? And even Hosford said, well, it cracked in 24 hours. Well, that could be corrosion, but 24 hours is pretty fast for corrosion, but it's not fast at all for hydrogen. Okay, so there's a story about deep drawing changed the properties fairly dramatically. Okay? I'm in and out for the next 3 days. Our next class will be on Friday. Jeremy, are they going to watch the rest of the videos on their own, or so let's take a vote. I mean, the videos are online for the casting class, and Jeremy, you've shown them too. How many people have gone ahead and watched the other videos? Okay, one of you. Good. Well, do you want to have Jeremy walk you through it at 11 o'clock tomorrow morning? And I would suggest that you just get online to eager.mit.edu and find the casting things. You've already seen the first 2, and there's about another 10 after that. And that's part of the course. Okay, you're going to watch 1/3 of the course by video. And so for the next 3 days, frankly, you ought to be able to finish up all of that this week or next week. Next week, I'm going to be down in Florida on Monday and Tuesday, and I'm tied up Wednesday. So we may have class on Thursday or Friday of next week. So right now, we'll have class this Friday, and then we'll probably have a class on Thursday or Friday, and then it's spring break. And sometime this week or next, I'll send everybody the schedule. In fact, if you haven't signed up for when you're going to make which week you're going to make your presentation, it's going to be, some of you are going to be making it the week we get back from spring break, the first week in April. So, but that's all you have to do for the course. Watch the other videos, make your presentation, and we should, if all goes well, be done by the end of April, even with your presentations. We're not going to videotape the presentations unless someone really wants to see themselves on video. But in general, I'm not going to put you on the web.